Good day, students. In my previous class, we are discussing about the torque on a current carrying coil, current loop kept in the magnetic field. And the formula tau is equal to mb sin theta. When a current carrying coil carrying current I, whose area A having number of turns n, then n into I into A is called M, magnetic dipole moment. And this current carrying coil, when it is kept in the magnetic field B, it experiences a torque. It turns. And this is actually the principle behind every motor. Every motor works on this principle. Conversion of electric energy to mechanical energy. You take an example of a motor of a fan. What is there inside the motor of a fan? There are two magnetic pole pieces. Simple way of expressing it. There are two magnetic pole pieces. That means between the two magnetic pole pieces there is a magnetic field. In between there is a coil. And in this coil you are passing current. You switch on. When you switch on, the current will go through the coil. So current carrying coil kept in the magnetic field experiences a torque and the coil will turn. It's simple mechanism. So this is the principle behind every motor. Conversion of electric energy to mechanical energy. Current carrying coil kept in magnetic field experiences torque. Now from motor, we'll move towards the meter. What is the principle behind motor and meter? Both are same. In motor also, when you pass current, coil turns. In meter also, when you pass current, the coil turns. Both principles same. But when you construct a meter, little bit you have to be more cautious because you are measuring something. In meter, we have to note two very important points. The first point is the proportionality. Current and angle should be proportional. For example, this is a meter, and in the meter scale, when you pass 1 amp current, if the needle gives a deflection of 30 degree, when you pass 2 amp current, the needle has to give the deflection of 60 degree, not 55. If it is 55, 1 amp when you pass, it shows 1. 2 amp when you pass, it won't show 2. Because it is not proportional. There should be a proportional in the current and the deflection, the rotating. That has to be important in the case of meter. Because we are measuring something. It can be any meter, maybe ammeter to measure current, voltmeter to measure voltage, speedometer to measure speed. In every meter, there should be proportional in current and the angle. Second one is the restoration. Restoration means what? For example, when you 1 amp current when you pass, it will turn by 30 degree. 2 amp current you pass, it turn by 60 degree. 3 amp current you pass, it turn by 90 degree. 1 amp 30, 2 amp 60, 3 amp 90. From 3 you make it 2, it from 90 come back to 60, restoration. From 2 amp you come to 1 amp, 30 degree. 1 amp you make 0, comes to original position, which is not there in the case of motor. You on the fan rotate, you switch off, again it come back? No. So in motor restoration is not there, but in meter there should be restoration. When you give current, it deflect. When you take the current, it come back to original position. They were taking into these two aspects. The meter is designed. Principle same, the torque on current carrying coil kept in magnetic field, same principle, but taking into consideration of the proportionality in deflection and restoration. So the first meter what was designed by a scientist called Kodialbail, and that was called moving coil galvanometer. Moving coil galvanometer. Moving coil galvanometer is the first meter which is designed. What the moving coil galvanometer consists of? First we'll see the construction part of the moving coil galvanometer. Then we'll see the working part of it, how it works, the theoretical part of it. First we'll see the construction part. Moving coil galvanometer consists of a rectangular coil which has got many number of turns of copper wire. A rectangular coil which has got many number of turns of copper wire. This is a rectangular coil, and this coil has got many number of turns, and this coil is suspended. The coil is suspended by means of a phosphor bronze wire. Phosphor bronze is a wire, a material which is a torsionless and twistless, twist free. You hold it one end, and when you turn from the other end, it turns. When you remove the force, it comes back to original position. Torsionless, twistless wire. Phosphor bronze wire. So, a rectangular coil made up of maybe copper, which has got many number of turns, copper wire, wound on a insulated frame. The frame should be insulation for that. And this is suspended by means of a phosphor bronze wire, and it is fixed here. You call it as a torsion head. Other end of the coil connected to a terminal T1. Torsion head connected to the terminal T2. This coil is suspended between two magnetic pole pieces. Two magnetic pole pieces, north and south. Therefore, this is the coil. Here we have magnetic pole piece. Here we have magnetic pole piece. This coil is suspended by a wire. Sorry, I am holding the wire like this here. This is free to rotate. This coil is free to rotate. Coil is not hold here. Coil is holding here from the top. So what is the construction part of it? There is a rectangular coil which has got many number of turns of copper wire wound on a insulated frame, suspended by a phosphor bronze wire, fixed at a point called torsion head. And that torsion head part is connected to the terminal T2, and this other end of the coil connected to terminal T1, for which you give electrical connections. The current what we have to measure, that is connected here. Terminal, a battery is connected here. When you connect a battery here, the current will flow through the coil and come back from here. The coil is suspended between the two magnetic pole pieces. This is north pole, this is south pole. Therefore, in between the two magnetic pole pieces, there is a magnetic field. So these are the direction of the magnetic field. So this is the direction of the magnetic field. This is the direction of the magnetic field. This is the coil. Just see here the picture. When you pass current, what happens? When you pass current, the torque will act on this coil. And what is the formula for torque? Tau is equal to mb sin theta. This is the direction of the magnetic field. Magnetic dipole moment is always perpendicular to the coil. Therefore, in this position, theta is equal to 90 degree. Sin 90 is 1. Torque is equal to mb. But when you pass current, coil rotates. When the coil rotates, the torque changes. If the torque changes, then you can't use this as a meter. Because if the torque changes, the rotating ability change. When the rotating ability change, you can't expect the proportionality. When the torque decreases, proportionality decreases. That means when you pass 1 amp current, if it turn by 30 degree, when you pass 2 amp current, it won't turn by 60 degree, it turn by 55 degree. Because for first 1 amp, 30, next 1 amp, only 25. Because the torque decrease. When you pass 3 amp current, next to 1 amp, it turn by 20 degree, so it is 75. If this is happening, you can't use it as a meter. So tell me how to change this? We have to make it proportional. That means when the coil rotates, the magnetic field also you have to rotate. See, when the coil is here, this should be the magnetic field lines. When the coil turns, this should be the magnetic field. See here, as the coil turns, magnetic field also turns. So what is the angle here? Theta, 90 degree, 90, 90, 90. Everywhere theta is 90 degree. Both sides. That means when the coil is here, this should be the magnetic lines. When the coil in this position, this should be the magnetic lines. When the coil is in this position, this should be the magnetic lines. For any position of the coil, listen, for any position of the coil, magnetic field line should be along the plane of the coil. If the coil is in this place, this should be the magnetic field lines. See the scale. When the coil turns, the magnetic field lines also turns. When the coil turns, the magnetic field lines also turns. That means for any position or every position of the coil, what is the value of theta? Theta value is 90 degree. Theta value is 90 degree. When theta is 90 degree, the torque is same. Tau is equal to mb sin 91. To make that, what is the alternative? I can just show here, if the two pole pieces are plane, this is north and this is south. If the two plane pieces are, the pole pieces, the north and south pole pieces, whose sides are plane, these are the magnetic field lines. And if you want to see the position of the coil, see if the coil is in this position, when the coil is in this position, theta value is 90 degree because this is the direction of the magnetic field and the normal to the coil is vertically down, and what is theta? 90 degree. But when the coil turns, theta value changes. Theta value changes. So in order to achieve, for every portion of the coil, the magnetic field line should be along the plane of the coil. The pole pieces are made concave in shape. Pole pieces are made concave in shape. If the pole pieces are made concave in shape, now the magnetic field lines in between is of this shape. Now somewhat the field lines will be along the plane of the coil, not exact. When the coil is like this, we have field lines here straight. When the coil like this, we have the field lines like this, see, somewhat. When the coil turns, these are the field lines. In between the two pole pieces, if you keep an iron piece, soft iron, it's a ferromagnetic material, highly magnetizable material, whose permeability is very, very high. It allows all the magnetic field lines to pass through it maximum. Whose permeability is very, very high compared to the permeability of air, which you study in the next chapter. Now if you keep an iron piece, soft iron, this is iron piece. Now the magnetic field lines will be like this. These are the magnetic field lines. When the magnetic field lines are like this, for any portion of the coil, see here, this is the coil. What is theta value? Say this is the magnetic field lines. Coil is here, theta 90 degree. Theta is the angle between magnetic field and normal to the coil. When the coil is like this, see along that we have magnetic lines. When the coil turns like this is the magnetic line. When the coil turns like this is the magnetic lines. For any position of the coil, the magnetic field lines along the plane of the coil, that means theta everywhere it is 90 degree, the torque is uniformity, there is a uniform in torque, uniform torque. This type of magnetic field line setting is called radial magnetic field. Radial magnetic field. Therefore, now we are going to slightly change the picture here. We are going to change the picture here. There is a rectangular coil which has got many number of turns of copper wire. Many number of turns of copper wire wound on a insulated frame, suspended by a phosphor bronze wire. It is fixed here, it is called torsion head, connected to the terminal T2, this end of the coil connected to terminal T1. The coil is suspended between the two magnetic pole pieces which are concave in shape. When I say concave in shape, it is not like this, it is like this. Just have a three-dimensional imagination. If this is the coil, one side of the pole piece like this should be, another side of the pole piece like this should be like this. Therefore, when you draw the picture, don't draw the picture like this. It is not correct. It is this picture. It should be like this. So, the pole pieces has to be concave. Concave means is it right? The two pole pieces are concave in shape. This is North Pole, this is South Pole. Both are concave in shape. And in between, we have a soft iron piece. An cylindrical iron piece can be placed like this. Cylindrical iron piece can be placed between the coil. And this is our coil. Is it right? So for this is the moving coil galvanometer. So moving coil galvanometer consists of a rectangular coil, many number of turns of copper wire, wound on a insulation frame, suspended by a phosphor bronze wire, fixed at a point called torsion head. Torsion head is connected to the terminal T2, and this end of the coil connected to the terminal T1. The coil is suspended between the two magnetic pole pieces which are concave in shape. In between the two magnetic pole pieces, inside the coil, a cylindrical iron piece is placed. The pole pieces are made concave and iron piece is kept to make the magnetic field radial. Therefore, what you understand when you look at this picture and look at this picture? This is the front view of the moving coil galvanometer. Moving coil galvanometer, when you see from the front, this is the view. This is a moving coil galvanometer. It is when you see from the top. See, when you see from the top, see, this is the circular iron piece, and these are the two pole pieces. Tell me, where is this part? This part is here, see, this is the part. It is coil. That's all. And this is the rectangular coil, and this part. And you can see that this coil is along the magnetic line, and this coil keep on turning. Even if at any position when it turn, when it come here, that also along the magnetic lines. When you come here, it is also along the magnetic lines. So wherever it is turning, it is along the magnetic field lines. Perfect, no? So this is the coil along the magnetic field lines. Now it is turning along the magnetic field lines, for any position because of radial magnetic field. So this is about the construction part of the moving coil galvanometer. Now we'll see the theory of it, how it works. As usual, I can just rub it off. This part I can rub. Connected to the battery, terminals you connected to the battery. Current flows through the coil. Current flows through the coil. The current flowing is, let it be I. We know the theory. A current carrying coil kept in the magnetic field experiences a torque. Because of that torque, the coil rotates. That torque we call it as a deflecting couple. We give a name, deflecting couple. Why it is called deflecting couple? Because of this couple, the coil gets deflected. It is just a torque what you studied previous. Deflecting couple. You are passing current in the coil, torque acts, couple acts, coil turns. What is the formula for deflecting couple? Tau is equal to mb sin theta. Tau is equal to mb sin theta. What is m? Magnetic dipole moment, which is given by the formula NIA. What is n? Number of turns in the coil. I, current what of passing in the coil. A, area of the coil. So that is m. What is B? Magnetic field between the two pole pieces. Theta. Theta is the angle between magnetic field and normal to the coil, or angle between M and B. Here what is theta? Here magnetic field is in this plane, coil is also along the same plane, so theta is 90, not 0, it's 90 degree. Theta is the angle between magnetic field and normal to the coil. So theta 90, sin 90 is 1. Therefore, that is NBIA. Same thing. M is NIA into B. So NIA into B. So NBIA. NBIA. So when you pass current, the coil turns. But see here, the coil is suspended and held by the torsion head. When the coil turns, because it is held here tightly, at the tip there is a twist produced. At the tip of the torsion head there is a twist produced because it is held tightly. And what is the advantage of that? When you pass current, the coil turns. But when you leave the current, what happens? The twist will make the coil to go back to the original position. You hold the wire at one end, from other end you turn, it gets twisted. When you leave, it comes back to original position because of the twist. So here also, when you pass current, coil rotate. Because of the rotation, there is a twist produced here, and that also will produce a couple called torsional couple. I call it a CT. Symbolically I call it a CT. And torsional couple is directly proportional to theta. For example, if the coil turns by 10 degree, there is a twist. If the coil turns by 20 degree, when the rotation is doubled, twist also doubled. It is directly proportional to theta. Therefore, CT is equal to C into theta, where C is called. What is C is called? C called couple per unit twist. Couple per unit twist of the suspension wire, which is a constant for a given wire. It will vary from material to material, it will vary from wire to wire, but this is a constant for a given wire. For a given wire, that is a constant. So now there are two couples. One couple, because of the current, will turn the coil one side. One, because of the current, which turns the coil. One, because of the twist. When the current is removed, the twist will make the coil to come back to original position. So deflecting couple will make it to rotate clockwise, means torsional couple make the coil to rotate anti-clockwise. Now when you pass current, the coil will not keep on rotate. It will come and stand at one place. So this is the initial position of the coil. When you pass current, the coil turns and come and stand here. Finish. Why it will come and stand here? Because in this position, your deflecting couple and torsional couple. Deflecting couple rotates like this. Torsional couple will rotate like this. At this position, both are balanced. And that is the place where the coil will come and stand. If you increase the current, what happens? When you increase the current, deflecting couple becomes more. Therefore, it will rotate still more, so that it becomes equals to torsional couple. When the current is reduced, what happens? Deflecting couple becomes less, but torsional couple is more. Therefore, little bit it come back. When the current is made zero, deflecting couple is made zero, it comes back to original position where torsional couple also zero. Therefore, whichever position the coil stand, coil rest in a moving coil galvanometer where deflecting couple and torsional couple are equal. Therefore, CD is equal to CT at equilibrium position. What is CD? It is NBIA. What is CT? It is C theta. Therefore, we can see that I is equal to C by NBA into theta. Just see the terminology. What is I? Current you pass in a moving coil galvanometer. C, couple per unit twist of the suspension wire. N, number of turns in the coil. B, magnetic field between the two pole pieces. A, area of the coil. Theta, the angle of deflection of the coil. For a given moving coil galvanometer, already a moving coil galvanometer is constructed. For a given moving coil galvanometer, all these are constant. C is the couple per unit twist of the wire, constant. Number of turns in the coil, fixed. B is the magnetic field, constant. A is the area of the coil, constant. Only changing is these two factors. Wherefore, then this is constant, then I and theta are directly proportional. And this is what we wanted. What is I? What current you pass in a moving coil galvanometer. And what is theta? How much the coil turns. When I am passing 1 amp current, if the coil turn by 30 degree, 2 amp current 60 degree, 3 amp current 90 degree. When you pass 1 amp current, if it turn by 7 degree, 1 amp current 7 degree, 2 amp current 14 degree, 3 amp current 21 degree, 4 amp current 28 degree. They are proportional. And this is the principle or the idea behind the construction of a meter. The current what you pass and the deflection produced, they are directly proportional. So this is called the moving coil galvanometer. This is called the moving coil galvanometer. Now theta by I, in this formula, the theta by I, theta by I. What is theta by I? Theta by I is equal to theta by I is equal to NBA by C. NBA by C. It is called current sensitivity. Current sensitivity. Current sensitivity is theta by I. Deflection produced when you pass unit current. Current sensitivity is equal to theta by I. That means current sensitivity is equal to theta when I is equal to 1. You can tell like that. Current sensitivity is equal to theta by I. Means current sensitivity is equal to theta when I is equal to 1. What do you mean by that? It's a deflection produced when you pass unit current. If more deflection produced when you pass unit current, then it is more sensitive. If less deflection produced when you pass unit current, it is less sensitive. For example, I have a moving coil galvanometer. You are passing 1 amp current. It turned by 30 degree. 2 amp current, 60 degree. 30 by 1, 60 by 2, 30 by 1, theta by I. 30 by 1, 60 by 2, it is 30. I have got one more moving coil galvanometer. When I pass 1 amp current, it turned by 3 degree. 1 amp current, 3 degree. 2 amp current, 6 degree. 3 amp current, 9 degree. It is not sensitive. It is not sensitive. Because even if you pass more current, the deflection is very less. The first one I told, 1 amp current, 30 degree, it is more sensitive. What is the advantage of this more sensitive and less sensitive? More sensitive can be measured. More sensitive device can measure even smaller value. Smaller value can be measured. Less sensitive, even if you pass a very small amount of current, it won't deflect only because it is less sensitive. Therefore, current sensitivity is the ratio of deflection produced per unit current, theta by I, theta by I. Or we can also call it as deflection produced when you pass unit current or ratio of the deflection produced per current. That is called current sensitivity. If you want to increase the current sensitivity, what you should do? Because theta by I is also equal NBA by C. Theta by I is also equal to what? NBA by C. So if you want to increase the sensitivity, current sensitivity, we should select the coil of more number of turns. We should select the coil of bigger area. Select a magnetic field strength should be more between the two magnetic pole pieces. The magnetic field strength will be more or stronger field, and the couple per unit twist of the wire should be less, because directly to NBA and inversely to C. It is called current sensitivity. Similarly, we have one more term called theta by I. Theta by I. It is called voltage sensitivity. Theta by V. It is called voltage sensitivity. Voltage sensitivity. That can be written as theta by IR, because V is equal to I into R. I is the current and R is the resistance. What is theta by I? It is called, theta by I is called IC. So IC by R, it is called VC. IC by R is called VC. Is it right? Therefore, so deflection produced per voltage is called voltage sensitivity. Deflection produced per current is called current sensitivity. Current sensitivity is given by the formula NBA by C. It is theta by I. Perfect. Next is how you measure theta in the moving coil galvanometer. In moving coil galvanometer, the deflection was measured with a very long process that is called lamp and scale arrangement. lamp and scale arrangement. What is lamp and scale arrangement? Lamp and scale arrangement means the wire, phosphor bronze wire, in which the coil is hung. On the wire there was a mirror. There was a mirror fixed on the wire. Say for example, if this is the coil, this is the wire, and on the wire there is a mirror. Little far distance somewhere here, we have a source of light. From the source of light, light come and fall on the mirror. From there it gets reflected. And here we have a horizontal scale fixed. Exactly in front of the mirror, there is a scale placed. So from light source, light come and fall on the mirror and reflect on the scale, horizontal scale. And when the current is not passed, this is the position of the coil, this is the wire and this is the mirror, and light is seen on the middle of the scale. When you pass current, coil turns. When the coil turns, the wire also turns, the mirror also turns. When the mirror turns, the light also will go like this. You can see, find the light there. So movement of the light, by seeing the movement of the light on the horizontal scale, you measure the angle, and that is called lamp and scale arrangement. So this moving coil galvanometer has got a lot of limitations. First limitation is, it is huge. Moving coil galvanometer is very big, a big circular coil suspended from the roof. One side we have pole pieces, and the side we have pole pieces. And second one is, it is not portable. You can't carry this because it is suspended and fixed. If you want to measure the current in your house, we can't carry this meter to your house. Your house you have to bring here, which is not possible. Meter means it should be portable. You can carry it. So moving coil galvanometer is not portable. It is fixed at a place because the coil is suspended by means of from one place, torsion head, fixed here. So not portable. Third one, definitely lot of defects in getting the readings, because whenever the readings are seen directly, the error is less. But as the readings is seen more and more indirect way, then the possibility of error increases. Therefore here the readings are seen using the lamp and scale arrangement. First you see how much the light has moved on the scale. Finding the distance of which the light moved scale, you see how much the mirror turn. How much the mirror turn will give how much the wire turn. How much the wire turn will give how much coil turn. So indirect method. More the indirect, more the error. So since it is seen through lamp and scale arrangement, the error possibility is more. Therefore what now we have, what we are using in our laboratory, that is a simple galvanometer which is called pointer galvanometer. Pointer galvanometer, or simply called galvanometer. Galvanometer. Pointer galvanometer or galvanometer. Just a basic difference I can tell. Constructional differences. Not all, very important constructional difference between the moving coil galvanometer and the galvanometer. In moving coil galvanometer, the coil is suspended by phosphor bronze wire. Whereas in pointer galvanometer or table galvanometer, we have the coil which is pivoted. Pivoted means what? This is a coil. You put a screw on the middle, and fixed on the base. But this coil is free to rotate, but you can't remove. It is pivoted. The coil is pivoted. Coil is fixed to the base, which cannot be removed, but it is free to rotate. It's called pivoted. So here coil is suspended. There the coil is pivoted. And we have concave pole pieces as usual. Concave pole pieces, and there is a cylindrical iron piece. This is the coil. So here coil is suspended, here the coil is pivoted. In the moving coil galvanometer, the torsional couple is given by the suspension wire. Because when you pass current, coil turns, a twist produced. When you pass current, coil turns, a twist produced. Because of the twist, when you remove the current, it comes back. Torsional couple is given by this twist, which is not there here, because it is pivoted. So we have two springs, hair springs, which are connected on the two ends of the coil. They are fixed to two terminals T1 and T2, which also act as a terminal for electrical connections. Whatever current you are passing, you pass to these two terminals. In the galvanometry model study seen in the lab, we have two terminals where we connect a wire. This is one terminal, another terminal fixed with a spring. So here what happens is, when you pass current, the coil turns. When the coil turns, the spring gets extended. When you remove the current, the spring comes back to normal position and coil comes back to normal position. So here coil is suspended, there the coil is pivoted. Here torsional couple given by suspension wire, here torsional couple given by two hair springs, very delicate springs. Two major difference. And one more is, seeing the reading directly. In moving coil galvanometer, the reading is seen using lamp and scale arrangements. But in galvanometer, the reading is seen using the needle which is connected on the coil. On the coil, there is a needle fixed like this. This is the coil, needle is fixed. And here there is a semicircular scale. When you are not passing current, the needle shows 0. When you pass current, the coil turns and needle will show different readings. When you release the current, coil comes back to original position, needle shows 0. When you reverse the current, the coil goes in the other direction. So there is a needle which is fixed on the coil, which moves over the scale. Which moves over the scale. This everything is made very compact. Put on the wooden board. Only so much part is seen, that is glass. Needle part and the scale. The other parts not seen. So here the coil is pivoted. Deflection couple, torsional couple by using the springs. Deflection is seen directly using the needle which moves over the semicircular scales. And this is called galvanometer, or whatever galvanometer we use in the lab. Understood? The modified version of the galvanometer, moving coil galvanometer is this. And this galvanometer is portable, you can carry, and it is very compact. This is huge, but this is very compact. Is it right? Okay. Thank you. With this, I'll complete today's class. Thank you very much.